So again, we might reasonably ask, we encountered a fractional exponent at an earlier example. What's going to happen if there's a square root involved in this expression, something like one of these limits? And in fact, a weird thing does start to happen. Unlike the polynomial over polynomial functions, it's possible to get more than one horizontal asymptote. And so what we're going to have to do is we're going to have to go back and let's redefine what's going on right here with this expression. One thing that we're going to need to help us is this definition right here. And we had this definition earlier on at some point in algebra, which states that anytime you take the square root of x squared, it's equivalent to taking the absolute value of x. And why is that? Well, don't forget, if we say absolute value of x, that's the kind of expression that gives us a number equal to itself if what we put inside of the brackets is greater than or equal to 0, and its opposite as long as x is less than 0. Right? So when we say absolute value of x, well, square root of x squared acts that way, right? If we put in the square root of negative 3 squared, it's the equivalent of taking the absolute value of negative 3, which is to say its opposite, the opposite of negative 3, algebraically, and that's positive 3. Right? Now I know this is a long chain of reasoning to figure out what's the absolute value of negative 3 squared under the square root, but it's important to note because we're going to use that principle here when we evaluate these limits, and let me show you how. Because we've got one square root of 1 over x squared, really the only way to get rid of something under a square root is to use the rule that tells us that the square root of a times the square root of b is equal to the square root of a times b, and the other rule for square roots, which says if you take the square root of a over the square root of b, that's equal to the square root of a over b. And what we said before is if we were to evaluate a limit that had a fraction, we had to multiply by 1 over x to the highest power in the denominator. Well, the highest power in the denominator is essentially 1 divided by the square root of x squared. And we would multiply that into the numerator and the denominator equivalently to give us something multiplied by 1. So now we think about what is the effect of that. Well, in the case of a square root, it's really equivalent to saying the following. We're taking the limit as x goes to negative infinity of. In the denominator, the quantity x squared plus 1, since it's under the root, can be combined with 1 over the square root of x squared, and that's just 1 over x squared. Since they're both under the square root, we can multiply it in equally. In the numerator, however, we've got x minus 1 times, from the definition, 1 over the absolute value of x. And that's important because look at where we're going. In this case, x is negative, right? We're letting x go towards negative infinity. So we're dealing with the part of the definition that says when x is less than 0, what do we do with that? In this case, that will be the limit as x goes towards negative infinity of x minus 1 times 1 over negative x. And that will make a difference for us in just a moment. Now, in the denominator, we're going to have this expression because 1 over x squared multiplies by x squared to give us 1, and 1 times 1 over x squared is 1 over x squared. Okay. In the numerator, we're going to get the equivalent of the limit as x tends towards negative infinity of 1x times 1 over negative x, that's negative 1, and plus, because of the negatives, 1 over x. Okay. And remember, we're still over the denominator that we've just rewritten as 1 plus 1 over x squared, which is by design. We want to do that so that when we substitute in negative infinity, we look at what happens to each of the terms individually. We get negative 1 plus something approaching 0 in the numerator. And we've got the square root of 1 plus something also approaching 0. Well, overall, that's negative 1. So this limit, as x goes to negative infinity, goes to negative 1. Let's try it with the other one. Now that we know the trick right here, we multiply in the numerator and denominator by the same type of quantity. That is 1 over the square root of x squared, which is essentially the highest power of the denominator. So by doing that, let's see what happens. That means that we're going to take the square root of x squared plus 1 times the square root of 1 over x squared. Right? Remember, the square root of 1 is 1. Let's see, that's divided into x minus 1 times 1 over its equivalent, the absolute value of x. Right? So now let's rewrite this once more. This is the limit as x approaches infinity of x minus 1 times, in this case, 1 over positive x, since x is greater than 0 now. Right? When we say x approaches infinity, it implies that x is greater than 0 this time. So it's 1 over x. And of course, in the denominator, we've got the square root of x squared plus 1 times 1 over x squared. So now we just carry out those multiplications. That's going to be the limit as x tends towards infinity of 1 over x times x, which is 1, minus 1 times 1 over x, that's 1 over x, divided by the square root of 1 over x squared times x squared, that's 1, plus 1 over x squared times 1, which is 1 over x squared. Making the appropriate substitution, that's 1 minus 0, divided by the square root of 1 plus 0, and that's going to become positive 1. So we actually have a horizontal asymptote of y equals 1 to the right and y equals negative 1 to the left, which is sort of interesting. In any case, we're not going to be graphing this quite yet, but we do know what this looks like now if we come across this situation.